Module 16, DNP3 testing, validation, and assurance, proving correctness before trusting operation. Number 16.1, why testing is central to DNP3 systems. In utility automation, correctness must be proven, not assumed. DNP3 systems interact with physical infrastructure where software defects can translate into service disruption, equipment damage, or safety hazards. Testing in DNP3 is not a post-development activity. It is an engineering obligation that validates protocol compliance, deterministic behavior under stress, interoperability across vendors, predictable recovery from failure. A DNP3 system is considered operationally trustworthy only after it has demonstrated correct behavior across defined scenarios. Number 16.2, layers of testing in DNP3 deployments. DNP3 testing spans multiple layers, each addressing a distinct risk class. 1. Protocol conformance testing. 2. Interoperability testing. 3. Functional and operational testing. 4. Failure and recovery testing. 5. Performance and scaling testing. Skipping any layer introduces blind spots that may only surface during live operation. 16.3, protocol conformance testing. Objective. Protocol conformance testing verifies that an implementation adheres strictly to DNP3 specifications, defined object groups and variations, function code semantics, error and exception behavior. This testing ensures that a device speaks DNP3 correctly, not merely approximately. Typical conformance scenarios. Conformance tests validate correct parsing and generation of frames, proper handling of unsupported requests, accurate CRC checking and rejection behavior, deterministic response formatting. A conformant device behaves predictably even when presented with malformed or unexpected inputs. Number 16.4, interoperability testing. Multi-vendor reality. Most utility systems are multi-vendor by design. Interoperability testing verifies that devices from different manufacturers interpret objects identically, handle optional features consistently, reject unsupported operations correctly. This testing moves beyond specification compliance into practical coexistence. Typical interoperability scenarios. One master communicating with multiple vendor outstations. One outstation interacting with multiple masters. Mixed implementation levels within a single system. Interoperability issues often arise not from errors, but from different interpretations of optional behavior. Number 16.5, factory acceptance testing. FAT. Purpose of FAT, factory acceptance testing, validates system behavior before field deployment when issues are cheapest to fix. FAT focuses on point mapping accuracy, object group and variation alignment, event generation behavior, control execution correctness. SHAT-FAT test coverage. A proper FAT includes static data reads, event polling by class, integrity polls, control operations, SBO and direct operate, time synchronization. All responses must be validated against expected semantics, not just observed values. Number 16.6, site acceptance testing. Transition to real-world conditions. Site acceptance testing validates system behavior under actual field conditions, including real communication media, environmental noise, real device timing behavior. SAT often reveals issues masked in controlled environments. SAT focus areas, communication stability over installed links, event buffering during outages, recovery after power cycles, timing behavior under load. SA confirms that laboratory correctness survives operational reality. 16.7, failure injection and fault testing. Engineering for failure, DNP3 systems must be tested under intentional failure conditions, including communication interruptions, device reboots, buffer overflows, timeout and retry exhaustion. These tests validate that failure handling behaves deterministically. Expected failure behavior. Under fault conditions, systems must reject invalid operations explicitly, preserve buffered event data, recover cleanly without operator intervention, avoid duplicate control execution. Unexpected behavior during failure is a design defect, not an edge case. Number 16.8, control operation validation. Safety critical focus control testing requires special rigor because it affects physical assets. Validation must confirm select before operate enforcement, correct timeout handling, rejection of stale or duplicate commands, accurate execution status reporting. Control paths must be tested repeatedly, not sampled. Hack negative control testing. Equally important is validating that controls do not execute when they should not. expired selections, unauthorized requests, invalid parameters. A system that refuses unsafe commands is as important as one that executes valid ones. TAPSH 16.9 Event Behavior Validation. Event correctness. Event testing must confirm correct classification into event classes, proper deadband behavior, accurate timestamps, correct buffer management. Event storms and event starvation must both be tested. Event loss prevention tests must verify that events are not lost during outages. Buffers drain correctly after recovery. Masters receive events in correct order. Event integrity is central to operational awareness. 16.10 Time synchronization testing. Temporal integrity. Time synchronization must be tested for accuracy after synchronization, stability over time, behavior during communication delays. Incorrect time handling undermines sequence of events analysis and post-incident reconstruction. STIL 11 Performance and load testing. Scaling validation. As systems scale, performance must remain predictable. Testing must evaluate polling cycle times, event throughput, CPU and memory utilization, network bandwidth consumption. Scaling issues are often nonlinear and must be observed empirically. Worst-case scenarios. Performance testing should include maximum event generation, simultaneous recovery of multiple devices, control operations during peak load. Systems must remain deterministic under stress. TAPSH 1612 Regression testing and change control. Impact of change. Any change to point mappings, event configuration, polling strategy, control logic requires regression testing. Regression tests ensure that previously correct behavior remains correct, no new failure modes are introduced, operational assumptions remain valid. In DNP3 systems, stability is a measurable property. TAPSH 16.13 Documentation as a testing artifact. Test traceability. Testing must produce artifacts. Test cases, expected outcomes, observed results. These artifacts support audits, knowledge transfer, future system modifications. Documentation is part of assurance, not bureaucracy. NABRA 16.14 Acceptance criteria and operational readiness. A DNP3 system is operationally ready only when it demonstrates protocol correctness, interoperability across vendors, safe control execution, deterministic failure handling, predictable recovery behavior. Passing basic communication tests is insufficient. Number 16.15 Why DNP3 testing is non-negotiable. DNP3's explicit semantics make it testable by design. This is intentional. The protocol assumes that engineers will test exhaustively, operators will rely on proven behavior, systems will face failure in production. Testing transforms specification compliance into operational trust. Number 16.16 Summary, proving reliability. Before depending on it, DNP3 systems earn trust through evidence, not assumption. Rigorous testing ensures that what should happen does happen, what should not happen never does. Failure leads to recovery, not chaos. In critical infrastructure, correctness is not a belief, it is a demonstrated property. Module 17, DNP3 Operations, Monitoring and Lifecycle Governance, Sustaining Trust in Live Systems. 17.1, From Deployment to Daily Operations. Once a DNP3 system is commissioned, its success is determined less by protocol design and more by operational discipline over time. Live utility environments are dynamic. Loads fluctuate, devices age, personnel change, and networks evolve. Module 17 focuses on how DNP3 systems are operated, monitored, governed, and sustained over years and decades without loss of reliability or trust. NASH 17.2 Operational Visibility as a core requirement. Knowing what the system is doing. A DNP3 system must never behave as a black box. Operators and engineers must have continuous visibility into communication health, event flow, control success and rejection, time synchronization status. Visibility is not optional. It is how silent failures are prevented. Observable protocol behavior. Operational monitoring should expose poll success and timeout rates, event buffer utilization, unsolicited response activity, error and exception responses. DNP3's explicit semantics make this visibility achievable if systems are instrumented correctly. 17.3 Communication Health Monitoring. Link and session awareness. Operational monitoring must track link availability, retry and retransmission frequency, latency trends, packet or frame error rates. Gradual degradation is often more dangerous than sudden failure. Early warning indicators. Rising retries, delayed responses, or intermittent timeouts often indicate physical media degradation, RF interference, network congestion, device resource exhaustion. Early detection allows corrective action before operational impact. ASHRAE 17.4 Event Flow and Data Freshness Oversight. Event throughput monitoring. Operators must know whether events are flow, whether buffers are accumulating, whether event classes are being serviced as intended. Event starvation or flooding both indicate misconfiguration or system stress. Data staleness detection. Masters should detect and flag stale static values, out-of-date event timestamps, loss of communication conditions. Freshness is as important as accuracy in operational decision-making. NAR 17.5 Control Operations Monitoring. Control accountability. Every control operation must be observable from request to outcome. Who issued the command, when it was issued, whether it was selected, whether it was executed or rejected. There must be no mystery actions in a DNP3 system. Control failure analysis. Rejected controls should be analyzed for authorization failure, invalid parameters, state conflicts, timing violations. Repeated failures often signal systemic issues, not operator error. 17.6 Time synchronization oversight. Temporal integrity monitoring, time drift undermines, sequence of events analysis, fault reconstruction, compliance reporting. Operational systems must monitor time offset between master and outstations, frequency of synchronization, failure of time update operations, long-term clock health. Some devices drift slowly and silently. Monitoring must detect trend-level degradation, not just gross failure. 17.7 Change management in live systems. Change as a risk event. Any change to a live DNP3 system, no matter how small, can have cascading effects. Changes include polling interval adjustments, event deadband changes, point database updates, network topology changes. All changes must be treated as controlled engineering events. Pre- and post-change verification. Operational governance requires clear documentation of intended change, validation in a non-production environment, post-change monitoring for unintended side effects. DNP3 systems reward caution and punish casual modification. TASH 17.8 Configuration Drift Detect. Drift as an operational threat. Over time, systems drift due to incremental configuration edits, firmware updates, emergency fixes not fully documented. Configuration drift leads to inconsistent behavior across sites. Drift control practices. Operational teams must maintain baseline configurations, periodic audits, comparison between expected and actual behavior. Predictability depends on consistency. ASHRAE 17.9 Incident Response and Root Cause Analysis. Deterministic Incident Investigation. DNP3 supports precise root cause analysis because all actions are explicit, all failures are reported, events are timestamped. Investigations should reconstruct communication state, event sequence, control actions, recovery behavior. Learning from incidents. Post-incident analysis should feed back into configuration improvements, monitoring enhancements, training updates. A DNP3 system improves through institutional learning, not guesswork. Number 17.10, Long-Term Maintenance Strategy. Aging infrastructure reality. Field devices age, communication links degrade, vendor support changes, operational governance must account for gradual performance decline, component obsolescence, planned replacement cycles. DNP3 stability allows infrastructure refresh without protocol disruption. Proactive maintenance indicators. Operational data can signal devices nearing capacity limits, links approaching failure, event buffers under chronic stress. Maintenance should be predictive, not reactive. 1711 Organizational roles and responsibilities. Clear ownership model. Operational success requires clarity on who owns protocol configuration, who authorizes control changes, who investigates incidents, who approves system modifications. Ambiguous ownership leads to unsafe systems. Knowledge continuity. Because personnel change over decades, governance must ensure documentation remains current. Operational assumptions are explicit. Training is repeatable. DNP3 reduces tribal knowledge only if organizations reinforce discipline. 17.12 Operational Metrics That Matter. Effective DNP3 operations track availability, communication uptime, event delivery latency, control success rate, recovery time after outages, configuration stability. Metrics must reflect operational reality, not just protocol activity. 17.13 Governance across the system lifecycle. Lifecycle perspective. Governance spans design, deployment, operation, modification, decommissioning. Decisions made early affect behavior decades later. Avoidance of operational debt. Short-term shortcuts create long-term fragility. DNP3 systems remain robust only when engineering discipline is sustained, governance outlives individual projects. Number 17.14, DNP3 as an operational contract. DNP3 functions as a contract between engineers and operators, software and physical systems, present decisions and future consequences. Breaking that contract through poor operations undermines system trust. Number 17.5, summary. Sustaining reliability is an ongoing act. DNP3 does not fail silently, but it can be neglected silently. Operational excellence requires continuous monitoring, disciplined change management, clear ownership, ongoing learning. In critical infrastructure, reliability is not achieved once. It is sustained daily through disciplined operations built on DNP3's explicit, deterministic foundation. Module 18, DNP3 as institutional knowledge. Why it persists, when it should be used, and when it should not. 18.1, DNP3 as encoded institutional memory. Over decades of deployment, DNP3 has evolved into more than a communication protocol. It represents institutional knowledge encoded in engineering rules, lessons learned from operating large, safety-critical, geographically distributed systems. Every constraint in DNP3 reflects a historical failure mode: silent data corruption, unintended control execution, loss of event history, ambiguous responsibility. DNP3 exists because these failures happened and because utilities needed a language that would not forget them. Number 18.2, why DNP3 continues to exist. Persistence rooted in fit, not fashion. DNP3 persists not because it is modern, but because it is correct for its domain. It solves a narrow, enduring problem, open quote, how to exchange operational data and execute control actions across unreliable networks without ambiguity or surprise. Close quote, this problem has not changed, even as technology around it has. Resistance to technological churn. Many technologies are optimized for throughput, flexibility, rapid evolution. DNP3 is optimized for determinism, explicitness, stability. In critical infrastructure, stability outlives novelty. 18.3. When DNP3 is the right choice. DNP3 is appropriate when systems require deterministic control behavior, explicit acknowledgement of success and failure, operation over unreliable or constrained links, long equipment life cycles, multi-vendor interoperability, auditable and reconstructible behavior. Typical use cases include transmission and distribution, SCADA, substation automation, field device telemetry, distributed automation requiring human oversight. Number 18.4, when DNP3 is not the right choice. DNP3 is not intended for high-speed protection messaging, bulk data transfer or streaming, self-describing device models, autonomous decision-making systems, rapidly evolving consumer or enterprise applications. Using DNP3 outside its design envelope introduces unnecessary complexity without benefit. Number 18.5, the discipline of choosing not to use DNP3. Good engineering includes knowing when not to apply a familiar tool. For example, protection schemes require sub-millisecond response, not request-response semantics. Analytics pipelines require throughput, not determinism. IoT telemetry platforms require elasticity, not strict control discipline. DNP3's strength becomes a weakness in these contexts. Number 18.6, DNP3 as a boundary definition tool. DNP3 excels at defining boundaries between observation and action, between automation and human decision-making, between operational systems and enterprise systems. These boundaries protect systems from unintended coupling and cascading failure. 18.7, human responsibility. Embedded in the protocol DNP3 assumes that humans remain accountable for control decisions. Automation assists but does not replace judgment. Failure must be explainable. This assumption aligns with regulatory, safety, and ethical realities of critical infrastructure. 18.8 Why DNP3 does not evolve rapidly. Stability as an ethical choice. Rapid protocol evolution can break legacy systems, introduce subtle incompatibilities, obscure accountability. DNP3 evolves slowly to preserve operational continuity across generations. Backward compatibility as a moral obligation. When infrastructure supports millions of customers, breaking compatibility is not a technical choice, it is a social one. DNP3 treats backward compatibility as a duty. 18.9 Knowledge transfer across generations. Because DNP3 behavior is explicit, documented, deterministic, knowledge can be transferred from one engineer to another, one generation of operators to the next, one vendor ecosystem to another. This continuity reduces institutional fragility. 18.10 DNP3 and the illusion of abstraction. Modern systems often promise abstraction, devices that just work, networks that self-heal, automation that optimizes itself. DNP3 rejects these illusions. It insists that someone must ask, someone must respond, someone must be responsible. Number 18.11 Why DNP3 feels conservative. DNP3 feels conservative because it is designed for environments where failure has real-world consequences, decisions are irreversible, responsibility cannot be delegated to algorithms. Conservatism is a rational response to irreversible risk. 18.12 DNP3 as a constraint that protects systems. Constraints in DNP3 slow things down intentionally, force explicit confirmation, reject ambiguous requests. These constraints act as guardrails, not limitations. Number 18.13 Institutional memory versus technological amnesia. Systems without institutional memory repeat mistakes. DNP3 exists to prevent relearning old failures, reintroducing unsafe shortcuts, forgetting why safety rules exist. It encodes memory in protocol behavior. The cost of ignoring a DNP3's lessons. When systems ignore DNP3's principles, common outcomes include hidden coupling between systems, automation without accountability, failures that cannot be reconstructed. These failures are not new, they are well documented. DNP3's enduring role in a changing world. As grids modernize, incorporate renewables, and adopt analytics and AI, DNP3 continues to provide a stable operational core, a deterministic control layer, a trustworthy source of ground truth. It does not compete with modern systems, it anchors them. Now 18.16 Final reflection. Why DNP3 still matters. DNP3 matters because it encodes a simple, enduring truth. Open quote, in critical infrastructure, clarity is safety, close quote. By insisting on explicit action, explicit failure, and explicit recovery, DNP3 protects systems not just from technical error, but from human overconfidence. It persists because the world still needs systems that fail visibly, recover predictably, and never pretend to be smarter than their operators.